getting it. See, I gave you faith, turned you down into hope. Can't deny it. Now I'm all alone and my joys turn them open. Tell me, where are you now that I made you?
Assalamualaikum. So today I want to explain about leg 4 3-phase synchronous generator. So the procedure summary. In the first part of the exercise, you will set up the equipment in the workstation. Connect the equipment as shown in figure 6.2 and make the appropriate settings on the equipment. In the second part of the exercise, you will vary the speed and field current and observe how this affects the no-load operation of a 3-phase synchronous generator. In the third part of the exercise, you will vary the field current of the synchronous generator by steps. For each step, you will record in the data table various electrical parameters related to the 3-phase synchronous generator. You will also vary the speed of synchronous generator by step while recording various electrical parameters. Then you will use the recorded data to plot various graphs and determine many of the characteristics of the 3-phase synchronous generator. Next, the equipment required is refer to the equipment utilization chart in Appendix C to obtain the list of equipment required of the exercise. Okay, the procedure. First, setting up the equipment. After that, install the equipment required in the EMS workstation. Mechanically couple the prime mover module to the synchronous motor. After that, on the power supply, make sure the main power switch is set to the 0 off position and the voltage control knob is turned fully counterclockwise. Ensure the power supply is connected to a 3-phase power source. Okay, this is the figure 6.2, the synchronous generator coupled to a prime mover. Okay, after we refer to the figure, we have to ensure that the data module is connected to a USB port of the computer. Connect the power input of the data module to the 24 volt AC output of the power supply. Okay, after that we on the power supply, set the 24 volt AC power switch to the on position. Next, start the data software LVDAC or LVDAM. Open setup configuration like file AC motor. In the metering window, select layout 2. Make sure that the continuous refresh mode is selected. Next, connect the equipment as shown in figure 6.2. On the synchronous motor generator, set the exciter switch to the closed position and the exciter knob to the 3/4 of maximum. After that, set the 4-quadrant dynamometer power supply or the prime mover to operate as clockwise prime mover. To do this, refer to the exercise 1 or exercise 1.2. Okay, this is for synchronous generator no-load operation. After that, turn the power supply on. Set the prime mover speed indicated by the speed meter in the metering window so that it is equal to the nominal speed of the synchronous motor generator. In the oscilloscope window, make the appropriate settings to observe the waveform of the voltage on channel E1, E2 and E3. That is the voltage induced across each of the stator winding of the synchronous generator. Okay, so for the question, are the waveform sinusoidal? So the answer is yes. Okay, what is the approximate phase shift between each of the voltage waveform? So the phase shift is 180 degree. Okay, after that, in the oscilloscope window, select the display continuous refresh function. Slowly adjust the prime mover speed until it approximately equal to 100 R per minute. While doing this, observe the waveform of the voltage on channel E1, E2 and E3 in the oscilloscope window. Okay, how do the amplitude Okay, this question is how do the amplitude and frequency of the voltage waveform vary when the speed of the synchronous generator is decreased? Briefly explain why. Okay, this is because the decreasing the synchronous generator speed decrease the amplitude and frequency of the sine wave voltage. Next question, does varying the speed of the synchronous generator affect the phase shift between the voltage waveform? Why? So the answer is phase shift is determined by the build of the motor, so it is not affected by varying the speed. Okay, after that, on the synchronous motor, slowly turn the exciter knob counterclockwise to decrease the field current. While doing this, observe the waveform of voltage on channel 1, channel E2 and E3 of the oscilloscope. How does the amplitude of the voltage waveform vary when the field current IF of the synchronous generator is decreased? Briefly explain why. So for the answer, the amplitude of the voltage waveform produced by the three-phase synchronous generator increases as the generator field current IF decreases and vice versa. Since the resistor and the supply voltage remain constant, so the voltage must be increased to compensate for the decrease in current. Therefore, the amplitude of the voltage waveform is increased. Okay, next, does the varying the field current IF of the synchronous generator affect the frequency of the voltage waveform and the phase shift between the voltage waveform? Why? So the answer is varying field current of the synchronous generator and phase shift is a set value determined when the generator is built. Okay, after that we can the question is set the prime mover to 0, then turn the power supply off. So the result for no load operation, you can see the graph for oscilloscope, the sine wave. You get the sine wave. So the channel data time base 5 millisecond per division. You can see the data in this table, channel 1, channel 2 and channel 3 all stated in the table. Okay, thank you.
So for characteristic of a synchronous generator, so we must modify the connection so that the modules are connected as shown in figure 6.3. So connect the three resistor section on the resistive load module in parallel to implement resistor R1. So the data will give for voltage 120 and then 220, after that same 220 and last 240. So for frequency for 120 is 60 Hz and then 220 we set in 50 Hz. After that we change the frequency into 60 Hz. Then for 240 frequency is 50 Hz. So for R1 we will known as infinity. So the frequency meter in metering window will be used to measure the frequency of the voltage produced by the synchronous generator. So first turn on the power supply and set the prime mover speed so that is equal to the nominal speed of the synchronous motor or generator. And then we will record the synchronous generator output, field current, frequency and speed. Then we will key in table data. These parameters are indicated by meter line 1, field, frequency and speed respectively. So change the value of resistor R1 and vary the setting of the exciter knob on the synchronous motor or generator to increase the field current to the value indicated in table 6.1. In step 10, that space are equally as possible. Note that it may be necessary to short circuit resistor in R1 to increase the field current to the maximum value. For each current setting, readjust the prime mover speed so that it remains equal to the nominal speed of the synchronous motor or generator, then record the data in the data table. So for volt and hertz 120 and hertz 60, for the voltage we will get 131.5 volt. Then the current we will get 370 milliampere, and then frequency we will get 83.50 Hz. Then last speed we will get 2503 Newton. So next, short circuit the resistor R1 using a connector lead. On the synchronous motor or generator, turn the exciter knob fully clockwise to set the field current I to maximum. Then the prime mover speed so that it remains equal to the nominal speed of the synchronous motor or generator. Then we must record the data in the data table. So set the prime mover speed to 0, then turn power supply off. So we must fill in all the table. So in the data table window, confirm that the data has been stored and title the data table as DT611 and print the data table. Then step 15, record the frequency of the voltage produced by the synchronous generator in the following blank space. This frequency is indicated in the column frequency of the data table. So for the frequency we will get 83.50 Hz. So next step we must calculate the theoretical frequency of the voltage produced by the synchronous motor or generator using the following equation. So this formula F equal to N XP by 60, then we will get 83.43 Hz. So the next question, compare the measure and calculated frequency. Are they approximately equal? So the answer is yes. In the graph window, make the appropriate setting to obtain a graph of the synchronous generator output voltage as a function of the field current. Entitle the graph as G611. Name the x-axis as synchronous generator field current. Name the y-axis as synchronous generator output voltage, and print the graph. So on this section, as the field current rise, the stator voltage increase proportionally. For most machines at about 80% of rated voltage. The curve become non-linear, showing the effect of magnetic saturation. If the straight line characteristic is continuous, the so-called air gap line result. And then in the short circuit test, the rotor is turned at rated speed with a 3-phase short circuit on the starter. As before, increase the field current, allow the plotting of the stator current versus the field current. A typical short circuit characteristic. The short circuit characteristic is linear. The flux density in the machine is very low since the terminal voltage is 0. The air gap flux is sufficient to produce a voltage to to overcome the leakage reactance drop. So in step 17, turn the power supply on. On the synchronous motor or generator, set the exciter knob so that the field current indicated by meter I is equal to the value given in table 6.2. And then set the exciter knob record follow the table 6.2 field current. So in 120 volt and 60 Hz, we will get the voltage is 160 volt, and the current we will get 500 milliampere. Then field current measured, we will get 500 milliampere, and then frequency we will get 82.64 Hz, and max speed is 2400 and speed is 2480. Then we will keep the same step with a voltage and hertz.
Next, we need to record the synchronous generator output voltage E0, field current, I field, frequency F, and speed N in data table. These parameters are indicated by meters E line 1, I field, IF, frequency, and speed respectively. Increase the prime mover speed to the value given in the following table by increment of 200 rotation per minute. For each speed setting, record the data in the data table. So the table will be shown. Okay, next. When all data have been recorded, set the prime mover speed to 0, then turn the supply off. In the data table window, confirm that the data has been stored, entitle the data as DT612, and print the data table. So this is the graph. In the graph window, make the appropriate setting to obtain a graph of the synchronous generator output voltage E0 obtained from the meter E line 1 as function of the speed N obtained from the speed meter. Entitle the graph of G612, name the x-axis as synchronous generator speed, name the y-axis as synchronous generator output voltage, and print the graph. I will describe how the synchronous generator output voltage varies as the speed varies. Okay, in synchronous generator, the speed of rotation of the rotor is equal to the speed of the rotation of the field at the stator. At excitation, field current, the voltage is directly proportional to the speed. The rate of change is proportional to both magnitude of the flux and the speed of generator. Thus, the voltage is directly proportional to the speed and the field current. Okay, next, in the graph window, make the appropriate setting to obtain graph of the synchronous generator frequency F obtained from the frequency meter as a function of the speed N which obtained from the speed meter. Entitle the graph as GC121, name the x-axis as synchronous generator speed, name the y-axis as synchronous generator frequency, and print the graph. Okay, I will describe how the frequency of the voltage produced by the synchronous generator varies by the speed varies. Okay, the frequency of the generator voltage depends upon the summer of field poles and on the speed at which the field poles are rotated. One complete cycle of voltage is generated in an armature coil when a pair of field poles passes over the coil. In one revolution of the rotor, an armature coil is cut by P/2 north pole and P/2 south pole. Since one cycle is generated in armature coil when the pair of the field poles passes over the coil, the number of cycles generated in one revolution of the rotor will be equal to the number of par of the poles. If speed increases, number of cycles covered by the rotor per second increases, and hence increases the frequency. Okay, 22. On the power supply, set the 20 volt AC power, switch off the off position. Remove all lead and cables. Okay, for the conclusion, in this exercise, you observe that a three-phase synchronous generator produces three sine wave voltage that are that phase shifted by 120 degree from each other. You saw the synchronous generator speed decreases the amplitude and frequency of the sine wave voltage. You observe that decreasing the field current of the synchronous generator decreases the amplitude of the sine wave voltage. You plotted the graph of the synchronous generator output voltage versus the field current. You plotted graph of the synchronous generator output voltage and frequency versus speed. This graph showed that the output voltage and frequency are proportional to synchronous generator speed. Okay, for the review question, the first question, most electrical power that is consumed today is produced by A. Synchronous condenser, B. Synchronous generator, C. Alternator, D. Both B and C. So the answer is D. Both B and C, which is synchronous generator and alternators. Okay. Question number 2. When the speed of synchronous generator is increased, A. The output voltage increases and the frequency decreases. B. The output voltage decreases and the frequency increases. C. Both the output voltage and frequency decreases. And D. Both the output voltage and frequency increases. So, the answer is D. Both the output voltage and frequency increase. Okay, next, for the question 3. Okay, the question, how does the field current affect the frequency of the voltage produced by a three-phase synchronous generator? Okay, for A, frequency increases as IF increases. Okay, B, frequency decreases as IF decreases. C, frequency is not affected by change in field current. D, both A and B. So, the answer is C. Frequency is not affected by change in field current. Okay, number 4, for the fourth question. The question is, multiplying the speed of an alternator by P over 60 allows the A. Theoretical frequency to be determined. B. Theoretical output voltage will be determined. C. Theoretical field current to be determined. Or D. Number of poles to be determined. So, the answer is A. Theoretical frequency to be determined. Multiplying the speed of an alternator by P60 allows the theoretical frequency to be determined. Okay, for the last question is, alternator is another name for A. Three-phase synchronous motor, B. Three-phase synchronous generator, C. Three-phase synchronous condenser, D. Three-phase AC to DC converter. So, the answer is three-phase synchronous generator. Alternator is another name for a three-phase synchronous generator. That's all from me. Thank you. Go run like that nigga. On the trigger